Okay, now we start the next module, module number 6. We shall look at a very special case of Sturm-Liouville problems, namely the vibrating string, and how the vibrating string give rise to a hierarchy of problems called the regular Sturm-Liouville problems. So, suppose we have got a string of length L and density rho x, and the string is stretched along the line segment 0 to L, and it is clamped at the two ends. So, you got a vibrating string clamped at the two ends, and the string is set into vibrations. Then what is the governing equation? The governing equation for standing waves is given by y double prime plus lambda rho xy equal to 0, equation 6.1 on the displayed slide, where lambda is a parameter. Now, along with 6.1, you need side conditions. 6.1 is an ordinary differential equation of the second order. Set of all solutions form a vector space of dimension 2. So, if you have to single out solutions, we have to give initial conditions, boundary conditions or whatever, but here the natural side conditions are the two boundary conditions. The string is clamped at the two ends do not move at all. So, y of 0 equal to 0 and y of L equal to 0. So, now what does this give us? A lambda for which a non-trivial solution exists for 6.1, 6.2 is called an eigenvalue of the boundary value problem. 6.1, 6.2 is called a boundary value problem. We are given a second order ODE and we are given two boundary conditions. So, it is called a boundary value problem, and there is a parameter lambda in the equation 6.1, and this parameter lambda will be called an eigenvalue if there is a non-trivial solution for 6.1 and 6.2, and the corresponding non-trivial solution is called the eigenfunction. And the form of the boundary value problem 6.2, the boundary condition 6.2 is referred to as Dirichlet boundary conditions. There are other types of boundary conditions which other types of physical problems lead to, and another popular boundary condition is the Neumann boundary condition, which is 6.3. Yet another boundary condition is the periodic boundary condition, and the periodic boundary conditions lead to the classical Fourier series when the density function is constant. So, the classical Fourier series can be thought of as a very special case of these regular Sturm-Liouville problems. So, there are three types of boundary conditions: the Dirichlet boundary condition, the Neumann boundary condition and the periodic boundary condition. We shall of course assume that the density function is positive and is continuous. Okay. So, let us begin with a simple example when the density function is constant and we take this constant to be 1. Namely, we take a string of uniform density, and let us also for simplicity take the length of the string to be 1. And so, the problem is y double prime plus lambda y equal to 0, and the boundary conditions are y of 0 is 0 and y of 1 is also 0. Now, we can immediately solve this differential equation. To solve this differential equation, you have to consider two cases: lambda equal to 0 and lambda is not 0. What happens when lambda is 0? The ODE simply becomes y double prime equal to 0. What are the solutions? A plus bx. Put in the condition y of 0 equal to 0. So, A must be 0. So, what happens? We simply get b of x. Put in the other boundary condition y of 1 equal to 0. What does that give you? B is 0. So, the solution becomes a trivial solution, the 0 solution, and that is not interesting. And so, lambda equal to 0 does not give you any non-trivial solutions. In other words, 0 is not an eigenvalue. So, now let us assume lambda is not 0. If lambda is not 0, then what is the characteristic equation? M squared plus lambda equal to 0. I root lambda and minus I root lambda are the roots of the characteristic equation. So, we get y of x equal to a cos root lambda x plus b sin root lambda x as the general solution. Now, let us put x equal to 0. When you put x equal to 0, y of 0 equal to 0 will give you immediately a is 0. And so, we are left with the condition b sin root lambda x, and when I put x equal to 1, I get the condition b sine root lambda is 0. Now, b is not 0 because we are looking at a non-trivial solution and a is already 0. So, b should not be 0 now. So, b is not equal to 0, that gives you sine root lambda equal to 0 or root lambda equal to plus minus pi plus minus 2 pi etc. Remember, lambda is not 0. So, lambda equal to pi squared, 4 pi squared, 9 pi squared, we have determined all the eigenvalues. The eigenvalues form a discrete set, pi squared, 4 pi squared, 9 pi squared etc. They form a discrete set, and this sequence of eigenvalues goes off to infinity. So, and the eigenfunctions are given by sine root lambda x, where lambda is pi squared, 4 pi squared etc. and we got a sequence of eigenfunctions. So, you have found the eigenvalues and eigenfunctions, and we know that sine pi x, sine 2 pi x, sine 3 pi x are orthogonal on the interval 0 to 1. That is classical Fourier analysis. Is this an accident? No, this is not an accident. It is actually a general fact. Whenever you take eigenfunctions corresponding to distinct eigenvalues, they will be orthogonal. So, let us formulate this as a general theorem, orthogonality of eigenfunctions, theorem 52 that you see on the slide. For the boundary value problem on 0 1 given by y double prime plus lambda rho x y equal to 0 with either Dirichlet boundary condition or Neumann boundary conditions, the eigenfunctions corresponding to distinct eigenvalues are orthogonal on 0 to L with respect to the weight function rho x. What does it mean? Integral 0 to L ux vx rho x dx equal to 0. The weight function is rho x. So, the density is rho x, and so the density gives rise to a mass rho x dx. Okay, let us prove this. We will do it only for the Dirichlet boundary conditions. The Neumann boundary condition is left as an exercise. So, if lambda and mu are distinct eigenvalues with eigenfunctions u and v, and we have the pair of equations u double prime plus lambda rho x u equal to 0, v double prime plus mu rho x v equal to 0, u of 0 equal to 0, u of L equal to 0, v of 0 equal to 0, v of L equal to 0. What do? What do you simply imitate whatever we did for the Legendre polynomials. Multiply the first equation by v, second equation by u, integrate over 0 to L, integrate by parts. So, what happens when you integrate by parts? The derivative will shift from one term to the other term. The second derivative will go on to the other term, one of the derivatives will go on to the other term. You will get minus integral u prime v prime in the first equation, and we will also get the same term in the second equation. When we subtract, this will go away. What about the boundary terms that arise when you integrate by parts? Look at the first one, v u double prime integral. When you integrate by parts, what are you going to get? You are going to get v u prime at L minus v u prime at 0, but v vanishes both at 0 and at L, so the boundary term vanishes. Similarly, for the second equation, the boundary term will vanish, so the boundary terms disappear. The other term that you get when the derivative shifts from one term to the other term, that also drops out. So, what is left over? You are simply left with lambda minus mu integral u v rho dx equal to 0. Now, lambda is not equal to mu, so lambda minus mu is not 0. Divide by lambda minus mu and you get integral ux vx rho x dx is 0, and as advertised. As an exercise, do the same thing for the Neumann boundary conditions. Now, next item is to understand the simplicity of eigenvalues. Now, recall from linear algebra, if you take a matrix A and if lambda is an eigenvalue of a matrix, it may happen that there may be several linearly independent eigenvectors corresponding to the same eigenvalue lambda. For example, take the identity matrix 1 0 0 0 1 0 0 0 1. What is the eigenvalue? 1. How many eigenvectors are there? Any three linearly independent vectors will serve as an eigenvector. So, the eigenvalue 1 has several eigenvectors which are linearly independent. In fact, in the example that I gave, 3. What about the corresponding story for the Sturm-Liouville problem? Suppose we have got a second order ODE 6.1, 6.2 with Dirichlet boundary conditions. Then to each eigenvalue lambda, there is only one eigenvector up to scalar multiples. In other words, if I take two distinct eigenfunctions corresponding to an eigenvalue lambda, they will be linearly dependent. This is what we mean when we say that the eigenvalues are simple. Let us prove this. Suppose that u and v are two linearly independent eigenfunctions with the same eigenvalue lambda. That means that u and v are both solutions of the same differential equation y double prime plus lambda rho x y equal to 0, and both satisfy u of 0 equal to 0 and v of 0 equal to 0. So, now we are in the following situation. We have got two linearly independent solutions of this second order ODE and they both vanish at the origin. So, what will happen to the Wronskian? The Wronskian will vanish at the origin, but how is that possible? When you take two linearly independent solutions of a second order ODE, the Wronskian must not be 0. If the Wronskian is 0, the two solutions are linearly dependent, and that is a contradiction, and that completes the proof that the eigenvalues are simple. The same result is also true for the Neumann boundary condition, and I leave it to you as an exercise. A slightly different argument is given in this slide using Picard's theorem, but that you can read by yourself, and so I will move on further. Now, we come to the completeness of eigenfunctions. Now, we state a theorem on the completeness of the set of eigenfunctions of the Sturm-Liouville problem with Dirichlet boundary conditions y double prime plus lambda rho y equal to 0, y of 0 is 0 and y of L is also 0. We assume that the function rho x is positive and continuous on the closed interval 0 L. The theorem states that the set of eigenfunctions are complete with respect to L2. Every eigenfunction is obviously a solution of a second order ODE, so it will obviously be continuous, and in particular it will be in L2. So, now we have got an orthogonal system. In fact, we have not normalized it. So, we have got an orthogonal system of eigenfunctions which will become orthonormal as soon as you divide by the length, and the question naturally arises, is this a complete orthonormal system for L2 of 0L? The fact that it is complete theorem, and you can find the proof of this theorem in Courant and Hilbert's Methods of Mathematical Physics volume 1 page 293, or you can look at Titchmarsh Eigenfunctions Expansions corresponding to second order differential equations volume 1. Titchmarsh proves it under substantially weaker hypothesis, and what happens is that here we give a slightly different formulation of it, which is what Titchmarsh really gives. We not only get L2 completeness, we also discuss the pointwise behavior. The point is, if you go back to the Fourier series, we proved that the Fourier series will not converge pointwise, but it will converge pointwise if the function is Hölder continuous or Lipschitz continuous, right? We proved these things. Now, the corresponding result for this more generalized situation. For the Sturm-Liouville problem in question, there is an infinite sequence of eigenvalues lambda 1, lambda 2, lambda 3. They are all simple, they go to infinity, and take the set of eigenfunctions phi 1, phi 2, phi 3, normalize them, and the set of eigenfunctions is complete in L2 that I already indicated. Here we talk about a slightly different version, the pointwise version. Every Lipschitz function f(x) can be written as a infinite series f of x equal to summation j from 1 to infinity Cj phi jx. That is, every Lipschitz function f of x can be written as an infinite superposition of these eigenfunctions phi 1, phi 2, phi 3 converging pointwise on 0L. The coefficients are of course the usual Fourier coefficients, and which is displayed in the last display in the slide. So, this theorem is a theorem on pointwise convergence, and the complete proof can be found in Courant-Hilbert or Titchmarsh's second volume. So, here are some exercises. Show that the eigenvalues of y double prime plus lambda rho y equal to 0 with boundary conditions y of 0 equal to 0 and y of 1 equal to 0 are positive real numbers. We already done this exercise basically. Determine the eigenvalues and eigenfunctions for the Sturm-Liouville problem y double prime minus 2y prime plus 1 plus lambda y equal to 0, Dirichlet boundary conditions at 0 and 1. And the third one is a Cauchy-Euler equation, x squared y double prime plus xy prime plus lambda y equal to 0. Now, remember that this differential equation is singular at the origin. So, the boundary conditions cannot be prescribed at 0. It will not be a regular Sturm-Liouville problem. It will be a singular Sturm-Liouville problem. What interval are you taking here? 1 upon e comma e, where e is the usual exponential functions e of analysis. So, on the interval 1 upon e, we prescribed periodic boundary conditions. Y of 1 upon e equal to y of e, y prime of 1 upon e equal to y prime of e. Solve the differential equations with these boundary conditions and determine the eigenvalues and eigenfunctions. The next one is a slightly atypical boundary condition. So, you are looking at y double prime plus lambda y equal to 0, y of 0 equal to 0, and this is an example of what is called as a Robin boundary condition. Y of 1 plus y prime of 1 equal to 0. The eigenvalues are given by lambda equal to k squared, where k satisfies the transcendental equation tan k plus k equal to 0. Use graphical argument to show that there are infinitely many roots. This problem is typically done in most books on engineering mathematics. You can pick up any of these books and you can look for the complete solution. This is a very popular problem which is available in most texts. To see how this kind of boundary condition appears in a physical problem, see this text of Byerly. This text of Byerly is a very comprehensive and old-fashioned but very useful text on Fourier series and boundary value problems. Now let us look at a slightly different type of problem, and we shall dwell a little detail on this problem. Take a rigid body in space and set it in rotational motion with fixed angular speed. The angular speed is fixed, but what you can choose is the axis of rotation. Pick a point, and of all possible axes through that point, how to choose the axis of rotation in such a way that the rotational kinetic energy is minimized. The problem is to formulate this mathematically. This is a physics problem. This physics problem must be formulated mathematically, and you must obtain conditions, the stationary condition for maximizing the kinetic energy. And what form do you get? You will get an eigenvalue problem, but this time it will be an eigenvalue problem that is familiar to you from linear algebra. Variational principles. You see, now we are going to show that the eigenvalues and eigenvectors, they enjoy a variational formulation. Now, whenever you look at problems in physics or geometry, these problems, they attain a state of maturity when you give it a variational formulation. Think of the classic theorems in physics which have evolved over the years. Take the Newtonian mechanics. Classical mechanics of Newton was given a variational formulation by Lagrange and Hamilton. The Lagrange and Hamilton's variational formulation of classical mechanics is susceptible to profound generalizations even for partial differential equations, for Schrodinger operators and other things. So, take the Fermat's principle in optics. It is a variational principle. In the theory of relativity, the light photons, they will follow a geodesic path. And what are geodesics? They are paths which minimize the lengths locally. Again, a variational principle. Look at the second law of thermodynamics. A system will evolve in such a way that entropy increases, a variational principle. So, you see that principles in mathematics, in geometry and physics, theorems in geometry and physics attain an advanced state of maturity when you reformulate them in variational terms as a variational principle. So, what the next problem is saying is that, so if you take a n cross n real symmetric matrix, then the problem of finding maxima and minima of these symmetric matrix is a variational problem. So, the problem of finding eigenvalues and eigenvectors of a real symmetric matrix has been given a variational formulation. We will take it up next time. We will look at the detailed proof of this variational formulation.